Hello, welcome back to another video, or I must just say that this is a live session. So, welcome to this live session on generative AI, and this session is a masterclass, which is specifically designed to cover all the concepts you need to know. It doesn't matter from which domain you belong to or from which specific domain you come from. This masterclass can help you get started with your career in generative AI. And I've specifically designed and curated the topics in this class to be as beginner friendly as possible. And this is to make sure that everyone is on the same page and that everyone can actually um, easily understand all the jargons that you guys have been hearing nowadays. So I'm relatively new to this live streaming setup, and of course, if I make any mistakes, I'm already apologizing to you guys in advance because just trying to get used to this new setup. And yes, if you have any questions, you can just leave them in the live chat, and hopefully I will be able to answer them. All right, so let's get started. Okay, so now the main question is, why do we need to learn generative AI, and why exactly is generative AI in so much demand nowadays? And we're going to understand this by first of all breaking down all the topics that we need to know about generative AI. And before we actually do that, it's important that we first understand the goals of generative AI. Like, what exactly is generative AI and what does it aim to do? We already know what artificial intelligence is. And most of the advancements in the field of artificial intelligence before 2020, from before the year 2020, were all associated with mimicking human intelligence or mimicking certain parts of human intelligence. Um, and they were focused on solving singular problems, like maybe I want to build a model for detecting objects, or I want to build a model to analyze sentiments from a given sentence, and so on. And I'm sure a lot of you must have already came across such models, and you must have even used such models in Python or in any other technological environment before. Generative AI has a broader goal. It is trying its best right now by looking at the advancements. And let me just make this clear that this is my own personal opinion. Of course, different scholars have different opinions on whether or not a generative AI targets artificial general intelligence. Now, in order to understand what artificial general intelligence is, we need to understand what generative AI is really doing. Um, artificial general intelligence says that we need to build AI systems which are um, basically going to mimic everything about the human behavior. So all the cognitive abilities that the human brain has, it should be able to mimic all those things using a certain model. It should be able to self-learn. So a model should not require additional training just to get familiar with newer or greater knowledge. And another part for that is that it should be able to generalize well on a large data set. Let me just quickly pop up the chat and see if someone has left any message. Okay, no messages yet. All right, so moving on. Why do we need to learn generative AI? And in order to answer this question, why do we need to learn generative AI? The why for every single domain, the why for every single field is different. So you might be coming from a software development background, or you might be coming from a content creation background. You might not just be a software developer. You might be a marketing guy, or maybe you are a customer support guy. Why is it important for you to learn generative AI? And the answer to that is I've basically given a little list here, and as you can see that if you're a software developer, artificial intelligence has already learned to write code, and this really impacts your job. If you're a content creator, artificial intelligence has learned to write blogs. It has learned to curate content. It has learned to synthesize even some advanced poster designs. I mean, I'm sure you must have already used softwares like the services like Midjourney, DALL-E from OpenAI. They're able to generate images. They're able to design very impressive posters, and that leaves a great impact on the content creation industry. And if you come from a customer support background, there has been a lot of advancement in the field of conversational AI, where different tech companies are building products uh, to basically allow AI systems to perform real-time communications using their voice, using a voice with any customers, and it's so effective that it can actually convert any of your lead into a potential customer. And this is why I believe I think this why justifies why do we need to learn generative AI in the first place. Okay, so in this session, I plan to basically cover these topics. Hopefully, in this 2-hour session, I am able to cover the basics of these topics. Of course, I'm not going to be going in much depth or technicalities behind how the models of work, how the mathematics behind the models work, because this is an introductory session, and I'm trying to keep things as generic as possible. I'm trying to keep things as off the shelf as possible, because I'm sure that you guys come from a different background, and in order to really understand generative AI, we need to first understand the basic concepts, and then we can actually jump into the more advanced details. Okay, so beginning with the evolution of AI, we need to understand how AI evolved, and where were we few years back, maybe let's say 10 years back, and where we are now. And we also need to understand what are generative models. We will be learning the modalities of the models, what are different types of modalities that the models support, and finally, the most rated topic of this whole session is large language models. What is an LLM and what are its parameters? We're going to go into the concepts like in context learning versus fine tuning. We're also going to be learning about prompt engineering. Of course, language models require effective prompting, so without prompt engineering, it's not possible to really do or to stimulate a certain behavior from large language models. Then we're going to be learning about an advanced concept which is on top of large language models, and that is how to build LLM agents. So there's a new concept in the market nowadays, and that is people are now using large language models as core controllers behind fully autonomous agents, and they're building these agents to be able to solve greater problems that large language models are currently not able to target. So we're going to learn the basics of large language model based agents, and then we're going to see some of the real world applications such as code generation, conversational AI that can be implemented using LLM based agents. And of course, we're also going to be looking at the benchmark and the metrics of open source versus paid models, and which one should we be using when we are building our projects. Okay, so let's move ahead. Okay, so when we're talking about generative models, it's important to understand there are two types of modalities in generative models. We have unimodal generative models, which means that each model consists of some sort of an input field or input stream, and then it produces some sort of an output. And additionally, each model can also produce a video or a video as an output, which means that unimodal models are basically capable of providing input streams, and they're able to provide output streams only for a certain data type. So unimodal models can either take in images and generate images. The unimodal models can either take in a video and generate another video, or it can take an audio and synthesize another audio stream. But it will only support one specific data type in its input and in its output. So most of the narrow AI models or deep learning and traditional deep learning and machine learning models were specific to the unimodal generative model category. So they were able to take in some specific data type, and they were able to produce some data as output. And the advancements in the field of generative AI led to the creation of multimodal generative models. Now these models are very interesting in the fact that they can actually take in any type of data as input, and then they can synthesize any type of data as output. And we'll be looking into some of the models, some of the popular models which can do this. And you must have already been using tools like ChatGPT, Gemini, Claude, and you know that these tools allow you to upload pictures and these pictures can then be so the model can basically generate description for these images for the pictures. So the model can also even process audio, and some of the latest models from OpenAI have even introduced the speech-to-speech model, which can actually take in audio and respond to you directly in audio. So the all of this is possible by the creation of multimodal generative models, and we'll be looking at them in a little detail in the upcoming slides. Okay, so after generative models, we know that what generative models are, but the the whole session, this whole session masterclass is going to revolve around um, the language models, because most of the advancements recently have been made in the field of language models. Of course, we have generative adversarial networks which are able to generate um, some images as well from a given image, and they can also generate text. But we are going to only study the language models because language models have been the most hottest models out there right now. So we're going to be understanding them. And in order to understand language models, we need to understand what were the advancements over the time period, over the history that have been made in order for us to be able to to witness such an impressive AI capabilities nowadays. This all started back in 1980, where a paper published something called recurrent neural network, which was basically a sequence model that used to take that was capable of processing text sequence, and it was able to classify that text sequence as positive or negative. And then this recurrent neural network was further modified and enhanced, and something called short-term memory network came in the year 1997. Then we came up with some advancements like word to vec, which was basically to represent words or sentences in terms of vectors. And this was a this was a major breakthrough, because this led to the models that we are seeing today. And most of the models that we see today, heads up, these models are not based on any of these architectures, and that's why I've highlighted the transformer and generative pre-trained transformer in green here. And the models that we are using in ChatGPT, Gemini, they are based on the advanced architecture introduced by Google in 2017, which is the transformer architecture. Now, the transformer architecture is a pretty complex architecture, and we'll be looking at its diagram. But I'm not going to go in much depth of it, because it revolves around a lot of mathematical computations, and it also requires us to understand how neural networks work internally. So the scope of this session is not to go in the details of those architectures, but to cover the overall concept of transformer, and just to understand transformer enough so that we can apply it to solve our own problems. Okay, so a transformer was a major breakthrough in the field of language models. And the major breakthrough that the transformer made is that it was able to generate text completions very well. So given a set of text or tokens to a model, transformer was able to effectively generate the next sequence of words from a given sequence of words. And OpenAI further improved this whole architecture, this whole model, and came up with something called generative pre-trained transformer. And so just to give you a little bit of background of the transformer architecture. So the transformer architecture was based on the encoder decoder architecture, which was introduced by Google. So the modifications made to the transformer architecture by OpenAI was the removal of the encoder and completely shifting it to the decoder. Um, just to simplify things, this whole strategy was to make sure that OpenAI, that the model could just generate text sequences really quickly from a given set of sequences. So that was the improvement that led OpenAI to bring out GPT that we all are using nowadays. Okay, so this is a pretty complicated diagram, and I took this diagram from the paper "Attention is All You Need" by Vaswani, which was published in 2017, and this shows the architecture of the transformer. And this is a major breakthrough. And as you can see, it's a pretty complex architecture, but what it's able to do has really changed the world, has really changed everything that we are basically doing nowadays. Okay, Moving on. So the advancement and the introduction of transformer architecture and later on GPT model did not stop there. A lot of companies and a lot of tech giants all came into this game, and they started bringing out their own models. Companies like Google, Microsoft, OpenAI, Facebook, Meta, all of these companies just introduced their own models, their own variation of models, tried to modify it, some existing architectures. They tried to make some changes into the existing architecture of these models and came up with models that were far more larger in terms of the number of parameters they were trained on. And thus in 2024 we know that we have models like GPT-4, GPT-4 Turbo, GPT-4o, and those were all advancements made one after another. Okay, so the the whole focus of this session is going to be around generative pre-trained transformer, which is the model introduced by OpenAI, because we need to understand what generative pre-trained transformer is and all its underlying details in order to understand generative AI. And I'm pretty sure that if you understand the concepts behind generative pre-trained transformer, you will be able to understand what the generative AI products are all doing, because most of the products that you see nowadays are basically using some sort of a technique that I will be discussing in the upcoming slides, and they're using those techniques to basically build advanced AI systems. But the underlying core controller behind all those advanced products is a generative pre-trained transformer or a GPT model, or simply a large language model, if I were to just keep this as simple as possible. And what does a large language model or a generative pre-transformer would do is that it takes a sequence of words, as I've discussed earlier, and it will produce some sequence of outputs. And as you can see in the example here, that if I provide Scooby Dooby Doo, the model will just provide, where are you? We got some work to do now. And this is just a very dumb example, a very naive example of what the model can do. The model is extremely good at producing text sequences, and this led to a lot of potential applications like text summarization, sentiment analysis. So the model, since it was trained on an extremely large data, although the only task it's performing is it's just completing the text sequence that you have provided, but it is now capable of actually generating sentiments for the text. It can use that same functionality to generate summarization for that text, and so on. You can like, the sky is the limit. And speaking of large language models, we need to understand some of the benchmarking metrics that are behind these models. Um, so a very common question that a lot of people nowadays ask is, if we were to implement our own application using these generative pre-transformers, um, what are the benchmark metrics or things that we need to look at to decide whether or not this model is good? And I have created a list for this. And if you look at this list, the top on that list are the number of parameters, and we're going to look at the number of parameters each model has. um, so the parameters, we will look at what parameters are, but there's another benchmarking matrix, which is the hyperparameters. And these are the parameters that the consumer of the models can actually control in runtime. Then we also need to know what context windows of generative pre-trained transformer is. um, and then we also need to look at whether or not these models are paid, which means that they are being consumed through a provided API, or they are open source, which means that you need to deploy these models in your own environment and manage all the scalability aspects of those models. The fifth part is that we need to look at the modalities the model supports. So what are the supported data types that the model has? Then we also need to look at the tool calling, which is an additional feature that many new models support, and that is that they can autonomously call tools, or a certain set of tools that you provide to them. And this actually introduces a new um, landscape of applications that the model can actually do. Okay, so the first thing is, what are the parameters? And I'm sure you must have heard this word before. And the recent news by OpenAI suggests and claims that GPT-4 model has 1.76 trillion parameters. which what does that exactly mean? So in simple words, parameters are mathematical representations of data and its relationships. And if you come from an NLP background, and if you don't worry about it. The basic idea is that we need to semantically relate data in such a way and store it in a mathematical form in such a way that whenever the model wants, it can basically find out what a relationship a certain word has with another word. And that is exactly what large language models have done. So the training data that on which large language models were trained on, that data consists of billions of such parameters. An example for those parameters can be understood by this diagram that I've presented here, is that let's say we have a word apple. So apple has some sort of semantic relationship with the word fruit, or the apple has some sort of semantic relationship with the word tree. Apple also has the color red. It is sweet, and it has some sort of relationship with Newton's law of gravity. Of course, this is a very simplified version of what large language models do, but just try to understand and try to visualize and picture that this graph, just imagine billions and billions of nodes like this, all connected, interconnected with each other. That's what a large language model looks like. It has billions of such parameters, and all of these parameters are basically tuned again and again and again until we get something like GPT-5, GPT-4, or GPT 3.5, 3.5 Turbo. These models have billions of parameters, and exactly how many of them? Well, we already know from the news, and OpenAI has already basically released a lot of blogs about their models, which claim that GPT-4 has around 1.6 trillion parameters, and GPT 3.5 Turbo model has around 175 billion parameters, which is a relatively older model. And of course, there are some trade-offs between these models, and we will be looking at them. And then we have some older models that were basically introduced by OpenAI quite earlier. And this one has 1.5 billion parameters, and as you can see, this is not as large as GPT-4. And one thing that you can look at from this little chart is that um, by each model, OpenAI is taking a huge step in terms of the number of parameters a model is trained on. And this is exactly why OpenAI this is exactly why GPT-4 has significantly outperformed GPT 3.5 in terms of tasks like code generation, um, um, content summarization, sentiment analysis, and the list goes on. Okay, so another concept that we need to understand is fine tuning. What is fine tuning, and why do we need to learn fine tuning? So large language models support something called fine tuning, and as opposed to retraining the entire model from scratch, what we need to do is we need to take a baseline model, which let's say we have GPT 3.5 Turbo model, and what we can essentially do is basically provide it as additional set of examples or data set, and basically run these batches of examples through this model and make it specialized for some specific task. Now, my personal opinion and insights on fine tuning is that you only do fine tuning when you have extremely large data set available. And let's just take an example of GPT 3.5 Turbo model, which has 175 billion parameters. In order to be able to make any little impact uh, or any significant impact on the parameters of a model like GPT 3.5 Turbo, you need to have at least hundreds of thousands of examples. Otherwise, that data will not make any impact on the model, and you won't get a significant difference. And a lot of recent studies and papers published, which basically compare the trade-offs and advantages and disadvantages of fine-tuning versus retrieval augmented generation, which is another advanced concept that we'll be looking at shortly, suggest that in context prompting is better than fine-tuning, which means that the knowledge provided to these models in the form of input or prompt is much more effective, and it stimulates the desired behavior much more effectively compared to fine tuning. And that is exactly why my personal opinion is that fine tuning is something that you do in very rare scenarios, and these models have been designed to perform better in context prompting. Okay, now, since we're talking about language models, it's wise to learn what effective prompting is, and we'll be looking at different prompting techniques are basically that are basically very important to understand if you want large language models to perform well, and to be able to, you know, provide, give you a desired behavior. An example for that would be, so you can see that I have presented a little example here which says ineffective prompt example, which is, let's say I want the GPT 3.5 turbo model to translate the word free into Urdu. So Urdu is another language. So you can see that this sentence, although sounds very specific and simple to us, but for the model this is not the very effective prompt. And a much more effective prompt would be to just convert this prompt into this format, and which would be like, let's say I provide a heading called instruction, and then I'm saying translate the text below to Urdu, and then I've provided the text. So now the model will effectively output the converted form, and we'll be looking at why this is better than this prompt. Okay, so some of the prompting techniques that we'll be looking at are zero shot prompting. We'll also be looking at few shot prompting, and then we'll be looking at chain of thought prompting and prompt chaining. So the first prompting technique that we need to understand is zero shot prompting. All models, all generative pre-trained models like Claude, Gemini, GPT, they all are designed to perform good or well on zero shot prompting, which means that we just simply prompt them with a certain question without providing them any additional context or data in the prompt, and expect them to just output the data. So this prompting technique is actually pretty simple. And let me just open. Okay, I hope you can see this screen. Yes, so we are on ChatGPT, and a simple zero shot prompt means that we just rely on ChatGPT to provide us certain set of information, and we completely rely on the parametric knowledge, which means whatever data ChatGPT was trained on, we rely on that information, and we rely that the model already knows that information. So that's what zero shot prompting is. So if we, let's say, ask it to write a sorting function in JavaScript. So the model outputs some sort of a code for us, and as you can see, it provided us with a bubble sort code in JavaScript, and I never provided any sort of example or demonstration of how to do this task. And of course this was a fairly simple prompt, and of course I was expecting the GPT to perform well on this, because I know that GPT model has been trained on a huge data set of different code bases. So I'm sure that the GPT model will provide me an effective code for my prompt. But what if I'm not sure that that the prompt that I have is the model is actually going to give me or the right kind of output, and I know that the model is not trained on the data? What do we do then? So another example, let me just go back to the PPT. So the next example is few shot prompting, which suggests that we provide example inside the prompt. And this type of prompting requires us to provide examples. So let's say I want the model to perform a task that it doesn't know how to perform. And an example would for this type of task would be to, let me just switch this window. So let's say I wanted the model to convert JavaScript JavaScript object into the following format, right? So I'm just going to ask the model to convert JavaScript object into the following format. So that would be to just say, and it's going to be object name, key name, key value. And just for the sake of example, I'm just going to say key value 1, key value 2, key name 2, key name 1, and I'll ask it to convert this object into the following format. And we know that this is a very specific use case, and of course the model hasn't been trained on this type of work. So that's why I'm providing an example, uh, and then the object would be, so we're just going to create a JavaScript object which is like this. So we're just going to say, um, let's say name, and that is Ali, and let's say we have an email which is test@test.com, and this is my object, right? So now when I tell the GPT model to do this, we're going to get the output as, so now it did not understood my prompt very well. So let me just rephrase this prompt to get my desired output. And what I will do is I will just change the keyword from convert to write the provided JavaScript object in following format, output. And then I'm also going to specify that it's an example, right? So I'm just going to say it's an example, and given object, so I'm just going to say object, uh, instead I just actually I'll just write JavaScript object so that it makes more sense. So now let's see, so it's still giving me the code. So in order to really fix this issue, I think it's because of the fact that I'm using the same window. So I'm just going to open up a new window to fix this problem, so that it doesn't remember the previous concept, the previous context that we provided it. So now when I just say this, so you can see that now that our output is name Ali, email test@test.com, and you can see that now we were able to steer a certain behavior of the model based on our example. And this was a task that the GPT model was not specifically trained to do. And in order for us to really stimulate this behavior in the model, we had to provide certain examples. And this is exactly what few short prompting is all about. So coming back to our slides, so this was a technique which says that we need to use few short prompting if we want the model to perform tasks that are not part of its parametric data. The next example, the next prompting technique is chain of thought prompting, and this is a very effective prompting technique, um, which allows us to basically solve complex problems and let the model solve complex problems. So let me give you an example for this. Okay, so what I can do, let me just open up a new window here in the GPT model. So now the chain of thought prompting technique, we just look at it again. The definition here suggests that we provide chain of inputs and outputs to or the conversation history that we had previously with the model, and then allow the model to learn from that chain of thought in order to be able to give us the preceding output. So how do we do that? Well, let me just quickly check in the chat and see if we have some questions. Okay, so I can see that we have some people who have tuned in. All right. Okay, so where were we? We were looking at chain of thought prompting. So in order to understand what chain of thought prompting is, we need to just simply go into ChatGPT again, And let me just create a prompt that kind of demonstrates how chain of thought works. So what chain of thought suggests is that we take in some sort of conversation history, or some sort of an example, and allow and let the model think step by step, instead of directly giving us the answer. So let's say, if I just say, if John had 3 apples and he ate one one, how many apples he has left. So this is a simple prompt, right? And if I ask this question, although this is a fairly simple task, but you can see that if I ask some tricky questions, the model will easily hallucinate. And in order to really fix this problem, what we can do is we can provide set of examples, and give it a chain of thought. So what I can do is I can just say, so this is a question, right? So I will just give it a question. Answer. The answer is would be the answer to this question would be 2, right? And how were we able to determine this? Well, the thought is, we had 3 apples initially, and we subtracted 1 apple from so John ate 2 apples, 1 apple left. uh Actually, John ate 1 apple, so we have 2 apples left, and therefore the answer is 2, right? And now I'll ask it another question, and this time I'm not going to give it any sort of thought or answer, and I'll see if the model actually follows the chain of thought that I've provided it. So I will say, if Mary had 3 laptops, one of them got destroyed, how many does she have left? Right? So now if I just pass this question to my model, let's see what's the output that we get. So you can see that the model provided us the thought, which is Mary had 3 laptops, one of them got destroyed. So the number of laptops is 3 minus 1, which is 2. So now it's using the chain of thought that I've provided it. And this prompting technique can be scaled to solve even more complex problems, such as mathematical equations where the model might hallucinate. So you can just provide as many examples as you want, and provide as many chains of thoughts you want, and then kind of utilize this technique to get better answers. And this technique has proven to actually outperform some fine-tuned models like GPT-4 and GPT 3.5 Turbo when they were tested against zero-shot prompting, the prompting technique that I just demonstrated earlier. So that's why it's so effective. Let's move on to our next prompting technique, which is prompt chaining. Now this is another prompt. This is another effective prompting technique. And before we actually dive into this technique, let me just open the chat and see if someone has messaged. Okay, we don't have any messages yet. Um, and we don't really have any questions. All right. So let's just proceed with our example. So the prompt chaining technique basically suggests that we use the output of the previous prompt as the context in the new prompt, and this is extremely useful. This technique is extremely useful if you want the model to be able to perform multi-step tasks, or perform complex tasks which require a lot of different steps. So an example for this would be to basically say, so I'm just going to open up a new ChatGPT window, and let's say I want the model to build a chat application in JavaScript. using React. So the this is the basic a prompt or task I have, and this is a high level task. I know that the model will not be able to immediately provide me the code for the entire application. We know because if I just simply just send this question or prompt to the chat GPT, um, and if you look at it, oops, I think kind of missed. So if you look at this right now, as you can see, that the question I asked was build a chat application in JavaScript using React, and the output was building in chat application. React involves several steps, and then it just kind of provided me a general level of steps. And this is not very effective because um, all of this output is not useful for me, right? It has a lot of additional text, and I don't need that. I just need the code, and I want this model to generate this application step by step, so that I can just effectively use that code and put it directly in my interactive development environment and just run the application. How do we do that? How do we allow this model to build the entire application while sticking to the main goal? And well, we can do that by simply saying, okay, so I will say here is the here are so I'm just going to say write build boilerplate for chat application using React, only provide file structure to me in your output. Okay, and now if I just pass in this prompt, the output for this would be, as you can see, that now the model provided me with the whole file structure, and this file structure is might be correct or might not be correct. Of course, we need to look at this structure in detail, but as you can see, now we also have some problem. As you can see that this whole output only has the should only contain the file structure, and right now we have some additional text as well. So how do we remove that? Well, we can just fix this prompt and say, so I'm just going to copy this prompt again, and I'm going to open up a new window, and I will just add additional details. Oops, I think I've copied the wrong text. So I'm going to copy this and paste it into another window, and now I will also say do not output anything except the required information. Okay, so we have provided an additional note to it. So I'm just going to say this is a note, and now we're going to just send this message. So as you can see, the model outputs only the file structure for us now, and we don't have any additional text associated with our output, and this is exactly what we need. So we are on the right track. So now what we can do is we can take in this entire file structure, and note that I'm always opening up a new window, and that is because the environment of ChatGPT allows us to retain conversation histories. So I don't want the model to hallucinate or perform based on the conversation history. I'm just trying to improve my prompting technique in such a way that whenever I provide it a zero shot prompt with an example, it should be able to do exactly what I say, what I tell it to do, right? So that's why now I'm going to take the output from the previous prompt, and then I'll say, here's the output, here's the file structure of the React application. And now in the next part, I will pass in another instruction. Remember that I told you that we need to use instructions as opposed to just passing in raw paragraphs, which are proved to be extremely ineffective. So that's why I'm passing in instructions below this file structure. So I'm just going to say generate code for all the files in the following format. And now what I will do is say, I will say, um, so I'm passing in some example like file name, and then I'm going to pass in, let's say, the code. And in order for the model to understand that I need the code for all the files, I'll just say that the format should be like this: file name 1, code 1, file name 2, code 2, and so on. So we want the code for all the files, so we'll just say file name n and code n. And let's see what we get. So now as you can see that the model is outputting the code for all the files followed by the file name. And as you can see that the code for the index.html is this. The code for favicon.ico file is this, because again this is an image, so this is a binary content. Of course there are some mistakes that the model made. We have a component of the React which is chatwindow.js, and you can see that we have basically the code for the files only, and it's even writing the CSS for us. And now you can see how powerful prompt chaining technique is. And this is exactly what chain of thought prompting and prompt chaining technique suggests, that we take in the output of the model, they take that output of the task, and then provide it to another prompt, and then get the desired output. And you can see that how powerful this technique is. And if I keep doing this iteratively, or maybe build a program that does this for me, I can I can basically build applications where the generative pre-trained transformer here would be able to write an entire application, an entire React application for me, um, without without even just by a single prompt. So this is what the prompt chaining technique is all about. So let me just head over the chat and see if we have any other questions. We don't have any questions yet. Okay, so I'm just going to continue with my slides. All right, so this was the basic introduction to the prompting techniques that we have. And again, this is just the tip of the iceberg. There are a lot of additional prompting techniques that we can use, and we will be discussing them as we progress into the more advanced techniques. And I will be definitely making and posting more sessions. But this was basically an introductory session, so I'm trying to keep things as simple as possible. Okay, so looking at all the things that we have done until now, we know that we have certain problems that we have faced with large language models. And if you have been an active user of ChatGPT or Claude or Gemini, you know that we have some problems in the models. So the first and the foremost problem is that the models tend to hallucinate as we keep prompting the models, or as we keep prompting the models to basically output different sort of completions. The models are going to hallucinate at some point. So some of the major findings about hallucinations is that usually large language models hallucinate when they don't have the knowledge that was asked in the prompt in their training data. So they basically provide false information, or they just try to complete your sentence with some useless information. And that's exactly what hallucination is. And this is a big problem. How do we fix this problem in large language models, right? If you were to rely on large language models, let's say I wanted to build a program using a large language model that basically generates applications, React based or Angular based or Python based applications for me from scratch. How do I make sure that the code that is synthesized by the generative model is reliable and that it can directly be executed? So if we have hallucination problem, we need to really fix this. Another problem that we have is short context windows. So the large language models have extremely short context windows. Of course, the newer models have improved this problem, and they have kind of introduced larger context windows, but there is still not enough. What if we want the model to remember what we set to it maybe like 2 months ago? That requires us to store a large conversation history, and the models at this moment are not able to retain conversation histories very well. And that's exactly why we need a mechanism to store these conversations. And this is a problem. This is an active problem in large language models nowadays. And another problem that we have is that the models do not have external knowledge. So let's say we wanted the model to to perform a task that goes beyond its own capabilities. The model can't do it because it does not have external knowledge. And of course, let's say we wanted the model to tell us something about an year that is not part of its training data. Let's say we were consuming a model which was the which had the last training uh, done on it in the year 2023, and what we wanted the model to basically give us an information that belongs to the year 2024. We will not be able to get that information because the model does not have external knowledge. And of course, the model cannot perform large tasks, large or complex tasks. And we've already seen that how we can steer that behavior by providing effective techniques. But you must be wondering, okay, so we've already used a prompting technique called prompt chaining. We have already used zero shot prompting, few shot prompting. Doesn't that solve that problem? Can't we just provide everything inside the prompt and let the model basically do its job? And the answer to that is, of course, if you were to build small applications, if you were planning on building small applications, we can do this. But when it comes to building effective or bigger applications, large language models alone cannot do enough. And that's exactly why a lot of recent studies have suggested something called the LLM agents. Now, this is a very advanced concept, and it's basically utilizing large language model as its core controller. And all of the advanced products that you see nowadays, which are built on top of large language models, including ChatGPT, Claude, Gemini, they've all been built on top of something called LLM agent. And what LLM agent suggests, the architecture of LLM agent suggests, is that we provide large language models with its own memory module. We provide large language models with its own planning module. We provide it with the capability of interacting with the environment or making changes to the environment so that it can perform actions and make changes to its external environment. Now, this is getting really powerful, and as you can see, that this technique right here is going to provide the large language models with the complete autonomy. And this would forever solve the problems that we have discussed in the slides, which is the hallucination, the short context windows, because now the models will have its own memory. The model will be able to store information in some sort of a database and then retrieve that information later on. And this will actually be very powerful, and you can just kind of imagine the applications that you can build with this. Then we also have its own planning module, so the model will always be able to plan tasks and try to keep track of the main goal as it keeps executing newer tasks, and it will always stick to the original goal. And this is also very powerful. And the last module, which is to basically provide model with a set of tools that it can autonomously call to perform certain tasks. So before we move further, I'm just going to look at the questions and see if we have any new questions or any new joinees. We don't have any new people here. Okay, so I'm just going to continue with the slides. All right. Okay, so moving forward with our memory module. So the large language model agent has something called the memory module, and the memory module suggests that we have two types of memories in the large language models. We have either a short-term memory, um, which is simply to store the conversation history. So whatever conversations I am having with a GPT model or a Claude or a Gemini model, I store that conversation history in some sort of an array, and that array will remain intact throughout the life cycle of my application. But as soon as the context of my application destroys, the memory will get destroyed and the data will be flushed. So this type of technique is great when we want the model to only temporarily remember the information, and of course, this is not good if you want the model to retain the information or persist the information and basically retrieve that information later. So for that, the memory module suggests that we have something called the long-term memory. Now, the long-term memory requires an additional construction of a data store, and this data store needs to be something called a vector store. a lot of studies have been introduced, and a lot of frameworks have recently came up. There is a framework called LangChain that suggests that we have something called the vector stores, and a lot of different implementation of vector stores have came up. Now what is this vector store? Well, this vector store stores something called embeddings. Now the concept of embeddings is relatively advanced, and I really didn't wanted to make this part of the scope of this session, but in general what embeddings do is they represent the entire information in some sort of a mathematical vectors, or mathematical representation or array of numbers, in which basically you store that information, you convert that information in some sort of you basically encode that information in some sort of embedding, and then you store that embedding into the vector store. So the vector stores are able to store a lot of embeddings, and then at any point of time when you want to retrieve that information, you give or pass a certain keyword. Let's say I wanted to search a certain keyword from my data store. What I can do is I can simply take that keyword, convert it into some sort of an encoding, and then pass that encoding, or basically compare that encoding with all the embeddings stored in the vector store, and then it will be able to quickly retrieve that information from the vector store and convert it back into text. Now this is a relatively more advanced concept, and we don't want to go into the details of this concept. And of course, I've kept this topic a part of my upcoming videos, as opposed to going in depth of this topic right now. Okay, so another I missed the file-based method, which is to basically store all the information in files, which is relatively slow because this involves basically comparing strings or searching through the strings of information. So this is going to be relatively slow because it has an additional computational overhead, where we need to search a certain text in a large knowledge base of text. And that's why it's recommended that when we're trying to build a long-term memory module in large language model based agents, we should be using vector stores, and we will be seeing how this long-term memory is effective as opposed to short-term memory in our upcoming videos, where we'll be constructing LLM based agents. Okay, so another concept that we have is the planning module. So I've already shown something called prompt chaining in my previous slide, but this is an advanced concept. This concept suggests that a large language model agent will simply break the entire provided task into sub-steps, and then it will keep iterating through this list and see on which step it basically is. So let's say if I have an input, say write steps to build a socket based chat application in JavaScript. Let's say I wanted to build this application. So what I will do is what the model will do is it is going to provide me with a set of steps, and let's say the step 1 would be to create boilerplate project, step 2 is to install dependencies, step 3 is to implement user interface. And then what I can do is take that one step and ask the model to only work on that step, and then break that step into smaller sub steps, and keep on iterating and seeing that whether or not it's able to meet the original goal, which was to build the chat application. And this is done by constantly iterating through the plan and seeing where do we stand in that plan. And that's how the planning module can effectively allow the LLM agent to automatically perform larger tasks, larger set of tasks without any human intervention. And we will be building large language model agents in our upcoming videos, and we will be seeing how is that possible. Okay, an additional functionality in large language model based agents is tool calling. Now, a lot of new models like GPT, Claude, Gemini, all of them have something called function calling. And this is basically introduced in the newer models. Let's say GPT 3.5 Turbo, Claude models that have been recently introduced by Anthropic. These models support something called tool calling. So the model, what it can do is, let's just take a look at this with an example. So I have an input which is, let's say, what's the weather in Karachi today? And I have provided my model with certain set of tools, which is, let's say, check weather tool, search internet tool, calculator tool, and so on. So the basic execution of the model would be that it will first of all, before providing any sort of completion or output to my prompt, it's going to just go ahead and give me a tool call, which is weather tool, because it knows that it needs to call tool. And how does it know that it needs to call the weather tool? Well, a large a large set of models like GPT 3.5 Turbo, GPT 4 Turbo, GPT 4, and other models have been trained to be able to effectively call these functions. And uh, that's why the model knows that if it has certain set of tools, it can basically call these tools autonomously at any point of time based on the provided prompt. And we need to let the model decide whether or not it should call the tool. And that's exactly why it's so powerful, because now, as you can see with this functionality, the model can become fully autonomous and perform or interact with the environment without the need for any human intervention. And as you can see in this example, the model automatically called the weather tool. The query of this model is that it's saying Karachi, Pakistan. So the model automatically figured out that Karachi is a city inside Pakistan. So it just entered this query, and the API of the weather tool basically resulted in 23 degrees Celsius. So then finally model took that output, added it in its knowledge, and then finally provided the output as the weather in Karachi is 23 degrees Celsius. And this right here is very powerful, and you can see that how it's able to basically convert an entire task into subtasks, plan the entire task and break it down, and it is also able to retain our conversations. So looking back at the problems that we saw in large language models, we know that problems like hallucination, short context windows, absence of external knowledge, or inability to perform tasks that require multiple steps can all be solved with LLM agents, and that's why it's so powerful. Okay, so um, this was it for this session. I was actually planning to keep this session a little longer, but I wanted to keep things short and as simple as possible so that we can go into relatively more technically advanced topics later in the videos. And so now I'm open to questions and answers. If you have any questions, you can just throw them at me, and I'll just go ahead and look at the chat and see if you have any questions. Um, I don't see any questions yet. Let's see if you have any questions. So while you guys ask the questions, I'm just going to reiterate through the whole slides and see what we have covered in this whole session. We covered the evolution of AI, how large language models came into the being, how different modalities are there, what are generative models. We learned them. We understand what parameters are, what is in context learning versus fine tuning. We also learned what is prompt engineering, and we looked at different techniques of prompt engineering. And we also covered large language model based agents, which are relatively more advanced uh, concept which takes in the concept of large language model and uses it as a core controller to basically provide it with modules like tool, memory, planning, feedback loop, etc. Okay, so Owais Shah has asked the question, and he said that will we be having more sessions? Yes, Owais, we will be having more sessions. And this is basically the part one of this whole series, and we'll be having more sessions as we progress. And this was basically a simple introductory session, which was only targeted for people who were just relatively new to generative AI field and just wanted to get familiar with the concepts and jargons that are out there in industry right nowadays. So that's why I kept it as short as possible. And as you can see in this plan of attack, I haven't covered the real world applications and the usage of open source and paid models, because I thought uh, I would just make this part of a separate video. Any other questions? I would just make this part of a separate video. Um, any other questions? Okay, so I guess that's it for this session. I'll be seeing you guys in the next one, and it's again going to be a live stream. And I'll try to cover some of the hands-on tutorial. That next session is going to be basically be on LLM agents, and um, I'm going to be covering the LangChain framework in that session. And in that session, I will also be exploring LLM agents and how to implement LLM agents using LangChain. Okay, so we have another question by Uwais, and he says, "Will we be making LLM agents by our own in the upcoming sessions?" Well, we will be using something called the LangChain framework, and we will not be using um, some open source models like Mistral or anything. We'll be using framework like LangChain, or maybe we'll be just consuming it via the OpenAI API. But I would, in my personal opinion, I think LangChain kind of helps us expedite the development uh, in terms of that it provides built-in memory modules and built-in planning modules, built-in agent wrappers that we can use to kind of quickly build LLM agents as opposed to building them from scratch. But just for the sake of this session, I might even go with the scratch from scratch example. But for now, I think it's better to just stick with LangChain. So yeah, that I hope that answers your question, Wes. But just for the sake of this session, I might even go with the from scratch example. But for now, I think it's better to just stick with LangChain. So yeah, that hope that answers your question. All right, so I'm just going to end this stream right here. And if you have any questions or if you have any concerns or if you have any feedback regarding this video, please don't forget to comment down below in the in after this video is published. And I'll be seeing you in the next one. Until then, bye.